Hey everyone, welcome to my presentation on active learning for natural language processing. My name is Robert Munro and I run the Bay Area NLP meetup group, but I'm here today hosted by the Hungarian NLP meetup group. And I know we've got a lot of other people from communities around the world joining us too. I'm aware of people in Australia, New Zealand, Japan, Malaysia, South Africa, all across Europe and all across North and South America joining us today. So I'm glad that you're able to take part today, no matter what time of day or even day of the week that you're joining us. And for the presentation itself, I've actually pre-recorded this component. So what that means, if you're watching us live on Zoom right now, not watching later on YouTube, if you're watching live on Zoom, I can take your questions as we go. They should be able to see me in the Zoom chat if you would like to bring that up. So I'm happy to take your questions via text on the Zoom chat as this presentation goes. And then we're also going to have time at the end. So at the end of the presentation, I'll be able to answer some of your questions live. Thanks to our hosts there. And so no matter what your background is, whether it's in natural language processing, whether you're an engineer who's interested in natural language processing, or if you're in an adjacent field like information retrieval or speech recognition or machine translation, I hope that there is going to be something interesting for you in this talk today. So the talk I'm giving is an excerpt from my book, Human in the Loop Machine Learning. And it's answering what I think is one of the most important questions in technology today. How can humans and machines work together to solve problems? And so those of you who work in machine learning know about 90% of machine learning applications improve with human feedback. They typically use supervised learning or something really closely related like lightly supervised learning. And human feedback can help machines understand confusing or new data. And this applies to a whole range of different use cases. So whether it's commands spoken that are sent to your smart devices, videos from the front of autonomous vehicles, or information extraction from healthcare-related messages. All these cases that I've worked on recently, additional human feedback increases the accuracy. So a typical human-in-the-loop feedback system could look something like this. You have a deployed machine learning model. You employ active learning, the main topic of this talk, to look at the most interesting items for human to review. Humans review those items, they create the annotations on those items, which creates the training data, and then you can create your machine learning model to be redeployed. You can also use transfer learning, and transfer learning is the process of taking existing models and adapting it to your case, to kickstart or to augment your machine learning algorithm. The focus on this talk, active learning, is important when you have a very large number of unlabeled data items and you might not have the capacity to employ people to manually annotate all of those items. So this comes from part 2 of my book, where I talk about different active learning methods, uncertainty sampling, diversity sampling, and advanced methods. I'll go through all of these in the presentation today. These chapters are already out, and then I'll give a sneak preview of a couple of topics from chapters 9 and 10, which are the next 2 chapters that I'll be publishing in the book, about advanced quality control and transfer learning methods that are very cutting edge and related to some of the interesting, more recent advances in active learning. So why would you use active learning? Accuracy is often cited as the main one. So let's say you have budget to annotate 1% of your unlabeled data. You want to make sure that it's the most important 1%. Speed is often another important factor. You want your model to be more accurate more quickly. And this has often been the primary use case for myself when I've used active learning in disaster response situations. I want to be able to translate or filter or extract information from messages following a disaster, sometimes in languages for which we have no existing annotations. And so being able to get a model up quickly and iterate on that is something that can help save lives. And so in that case, it's less about the amount of human input, more about the speed of getting a good model out as quickly as possible with all the data that we can feasibly annotate. And then finally, diversity. So unless you're looking at academic data sets, a random sample of unlabeled data is typically biased. The unlabeled data that you have available to you, your raw data, would typically be oversampling from some data source. And a lot of the time that data source may be itself overrepresenting more privileged people. In natural language processing, the most obvious use case is when you have large amounts of text data. English will tend to be overrepresented. English only makes up about 5% of the world's conversations daily, but it makes up a much larger percent of almost all text data sets which are out there. And so selecting through different languages is fairly easy with language identification. We can have more subtle but equally problematic ways that your data might be biased. So before I start, I'd like to debunk 3 active learning myths, which are very pervasive. One is that active learning and random sampling converge with enough data. And so this is only true on academic data sets where active learning is simulated. The argument here being that you don't need active learning if you have enough budget, because once you've annotated, say a few 100,000 items, your model is going to be just as accurate from random sampling as it was from using active learning. This simply isn't the true unless you only started with 100,000 items. Unfortunately, academic data sets are randomly sampled. So maybe an academic data set has 100,000 items, which were randomly sampled from a pool of 1 million items that you no longer have access to or the ability to create labels for. So if you look at a lot of academic papers which are simulating active learning, it can mislead you as to the effectiveness of active learning. Another is that uncertainty is tractable and can be read directly from softmax. So I've seen people as prominent as Jan LeCun claiming this recently, and this simply isn't the case. So if you have a binary classification task, you can read the confidence directly from your softmax output, but anything more complicated than a simple binary classification task means that there are multiple different ways of calculating uncertainty. And no one way is guaranteed to be the most optimal way for your data. And calculating the optimal uncertainty for anything beyond a binary task is an optimization task in its own right. In fact, a lot of the advanced uncertainty sampling methods are themselves machine learning algorithms. Finally, related to uncertainty, one of the myths is that softmax base of E, Euler's number, is a special case of that number. And that simply isn't the case. In fact, if you converge your model with a different softmax value, you'll get the same model optimization. And so this isn't a case where Euler's number is special. And while changing the base, or equivalently the temperature of your softmax output, won't change what is the most confidently predicted item, and therefore won't change your accuracy, it can in fact change the rank ordering of items. So what is the most uncertain item from your pool from one base, or equivalently temperature from softmax, will be different if you change that. And you'll find this myth perpetuated out there. This is a special case for Euler's number when it is not. And you'll also find that almost all of the active learning literature ignores this as an additional parameter that needs to be looked at. So while the second two of these myths here do make active learning a more complicated problem than many people assume going in, it also makes it a more interesting problem as well. It's a new area where we can look at models. These models are inherently looking at the interaction between machine learning uncertainty and human understanding. And so any time spent working on these kinds of problems teaches us a lot about how humans and machines can solve problems together. Before I jump into the methods themselves, I want to give an idea of how popular active learning and human-in-the-loop processing is right now. So I'm going to go through 10 examples here and the benefits that come from using human-in-the-loop machine learning. So avoiding bias. AI will have biases which are different to human biases, and so having a human in the loop of decision making is one way to avoid biases in both humans or AI. It's also a way to create employment. So by some measures, the majority of people working in machine learning are creating training data. Actually, more people labeling data than creating algorithms for artificial intelligence. And when done properly, creating employment for human labeling can become a great way of bringing people into the information economy who previously wouldn't have been able to work in the information economy. And again, when done properly, quality controls can be a lot more egalitarian. So the demographics of a person should not necessarily affect the quality of their task, meaning that it's more of a meritocracy in terms of being rewarded for your work. Human-in-the-loop processing is also important for augmenting rare data. So in this example at Facebook, looking at misinformation, you can imagine that for very rare languages, there isn't even enough unlabeled examples to build training data sets. Certainly not enough to get to the same level of accuracy as for a language as English. And so having a human in the loop can augment rare data and is another way of avoiding bias. In this case, bias towards the amount of available training data. Human-in-the-loop processing is also a great way to maintain high precision. It's a really good example of autonomous vehicles, in this case helicopters. So you certainly don't want a helicopter to ever fall below human level accuracy. And they're interested in UX implications about what's the right way for a machine to back off to a human and tell the human that needs to take over. Similar to pilots and helicopters, human-in-the-loop machine learning can be used to incorporate subject matter experts. So in this particular example here, it's experts in looking at surveillance of potentially illegal behavior in markets, and human-in-the-loop machine learning enables these experts to create training data in ways that would not be available to non-experts and keep them employed in this process. Similar to this, in auditing use cases, you need consistency and accuracy. This might be court-ordered. And so while you do need machine learning to scale, you also need to ensure that you maintain human-level consistency and accuracy. And related to this again, human-in-the-loop processes can make work easier. So in this example of cybersecurity, it's automating some of the tasks that a security analyst is able to work in, but not necessarily all of them. And related to making an expert more efficient, but not necessarily replacing them, in a lot of medical use cases, we're seeing doctors and other healthcare professionals use machine learning as part of their decision process, but not being replaced by it. Finally, you can use human-in-the-loop machine learning to provide transparent accountability and increase safety. So in this particular example for visa applicants, the system backs off to a human only in the negative case. So if an automated system rejects someone's visa, that's double-checked by a human. So this is a use case where some of the outputs they're happy for or willing to accept some false positives going through. So maybe people getting visas that shouldn't have. But for the negative use cases, they're not going to allow those to necessarily affect someone's life without further human review. And finally, is kind of a fun use case where Formula One is testing changes to the rules using people playing eSports, using gamers to test out those changed rules and look at the safety implications there. And so all of these use cases you just looked at were reported within 1 month of each other. So hopefully this gives you a really good idea of how widely adopted human-in-the-loop machine learning is right now. Certainly we hear about a lot of different kinds of advances in AI and in NLP in particular, with a lot of really fun advances recently in pre-trained models. But certainly there are no recent advances that you can point to that are being so clearly adopted across so many industries in the real world. And obviously, something that's really missing is a lot of information about how to implement these different methods. Not many people get taught about active learning or human annotation in their undergraduate courses. And I think this is a real gap that I'm trying to fill with my book. So one way that you can think about these different methods is in a knowledge quadrant, where your known knowns, your known unknowns, your unknown knowns, and your unknown unknowns. And so to go through all of these in turn, your known knowns, your current model is confident predictions. So anything your model is confidently predicting and getting correct, these are what your model knows that it knows. Your known unknowns is what your model knows that it doesn't know. So if you have a binary classification task, these are everything that are around 50% confident, everything right at the decision boundary. So your model knows that it's uncertain in these particular cases, and this is where we use uncertainty sampling. one of the types of active learning that we'll talk about today. Uncertainty sampling targets items near the decision boundary. Your unknown unknowns, needless to say, are harder to identify. So how do you know when you don't know something? These are gaps in your current model knowledge. And the set of methods for trying to work out what you don't know that you don't know are known as diversity sampling. And we'll go through some examples of these in today's talk as well. And we're only going to touch on it briefly, but to round out the quadrant, transfer learning are your unknown knowns. So what latent information is there in related machine learning models they don't know is there yet, but if you adapt to your current problem, might be useful for increasing your model's accuracy. So to begin with, we're going to look at uncertainty sampling. So when your model is confused and you want to sample those items because those are the most likely to be predicted incorrectly, because the closer the decision boundary, the most likely to move that decision boundary if they are currently incorrect. So here's an example of a simple binary task. We have label A and label B. And uncertainty sampling should ideally target these 5 items with the question marks in the middle of them. So these have been selected to label because these are the 5 closest to the decision boundary. So active learning, you might apply your model to millions and millions of unlabeled items, and then you're selecting those which are, in this case, the most uncertain. And for our worked example, let's assume that we have a 4-class prediction task, shown here on the left, which could be expressed as a PyTorch tensor here on the right. So we've predicted y0, y1, y2, and y3, and the most confident item is 64.39% with our 4 labels. And we can build on this typical output from softmax, known as a probability distribution, and to look at different kinds of uncertainty sampling. Just to flag, the outputs of softmax are not strictly probabilities, but when you have outputs that sum to 1, this is known mathematically as a probability distribution. I go into more detail about the pros and cons of softmax in my book, but I won't go into more detail in the talk here today. So the most commonly used uncertainty sampling method, and probably one that you have used in the past, is least confidence sampling. And so this is simply looking at the difference between the most confident prediction and complete confidence, 100% confidence. So here our most confident prediction is 64% confident, and we are able to take that and know that because there's 4 items, it couldn't be less than 25% confident. That's the minimum. So here we just have that denominator as a normalizing function to give us a 0 to 1 range, where range is where 1 is the most uncertain. And all of our methods will be in a 0 to 1 range. So this is something I highly recommend. Otherwise, you will get different ranges from different uncertainty sampling methods, and in some 1 will be more uncertain, and in others 0 will be more uncertain. And if you don't remember to normalize them, you're going to get into a lot of trouble in downstream processing. And also, depending on the type of method you're using, some downstream processors will assume a 0 to 1 range. So margin of confidence is the difference between the top 2 most confident predictions. So this is also something you might have used in the past. So here, the most confident prediction is 64%. The next most is 23%. So we're looking at the difference between them, and again, normalizing for the maximum possible difference. Related to margin of confidence, ratio of confidence looks at the ratio between the top 2 most confident predictions rather than the difference. And we don't need to normalize this because the smaller of the 2 divided by the larger of the 2 is already in a 0 to 1 range. This is actually more mathematically well motivated than taking the difference. It's more mathematically well motivated to take ratio, but it's rarer in the academic literature. And this is mainly because the methods predate the current types of machine learning algorithms that we're using. But even though ratio of confidence is rarer, this should actually give you a more accurate indication of the difference between the top 2 most confident items. Finally, entropy uses information theory to look at all of the predictions. So in this case, it's looking at the difference between all of these predictions and predictions with no information, which would be the case that they were all 25% confident. And so entropy takes into account all of the predictions, not just the top two or the top one, like you saw with least confidence predictions. And so any of these four methods might be the most appropriate one to use with your data, and you don't know without testing. So you should try out these different methods if you're using active learning and see what's right for your data. To get intuition for what these different methods do, you can play around with it, and I'll share this link in the chat as well at my website here. So if you go to that site, you can click and make your own labels. Here in the top left, we can assume that we have 3 labels. These are the 3 black dots. And here are how these 4 different methods for uncertainty sampling pattern. So you can see that the 2 that look at pairwise confusion, margin of confidence, and ratio of confidence, we have these long bands coming out where pairwise confusion is enough. You can sample the uncertain items there, the most red items. Whereas entropy, which looks at confusion across all of the items, it concentrates where it samples right in the middle of those 3. At least confidence falls somewhere in between. You kind of get a secondary effect of looking only at the most confident, that it effectively also takes into account the other items as well. And if you look at the right-hand side in the 4 examples here, you can see that with a large number of labels and a relatively random pattern, the area of items that will get sampled as being the most uncertain are very, very different. And so it's really important to think about what are the right methods that might be right for your data to get an intuition for what kind of confusion is most important to you. Is pairwise the most important? Is it confusion across all your labels? And that can often be the best starting point for deciding which of these heuristics is the best one to begin with for uncertainty sampling. And then you can think about trying the other methods and also building out some of the more complicated uncertainty sampling algorithms on top of them that we'll be looking at later. There's also some interesting, more recent techniques using Monte Carlo dropouts. And so you've probably done this in training your models before, randomly dropped out certain neurons during the training process so as not to overfit your model, applying the same technique at prediction time and then getting multiple predictions across the models with different dropouts, sometimes known as Bayesian deep learning. And it's called that because if you squint at the range of predictions that you get, it'll look like a normal distribution or a Gaussian distribution. That's somewhat pretentiously called Bayesian deep learning. It's certainly like a great method to use if, for example, you don't get reliable confidence estimates for your predictions because of the type of architecture you're using. And you can look at variation in terms of the actual model outputs, the logits, or even just the labels themselves, if that's all you have access to. So look at the items which are the most variable in the labels. And this builds on a long history of using ensemble methods, which is sometimes called uncertainty by committee in active learning literature. So that's uncertainty sampling. We're now going to move on to diversity sampling. So diversity sampling is trying to find what you don't know that you don't yet know. So these are gaps in your model knowledge. And the hard thing is obviously you don't know in advance what you don't know. So to go back to our example of the binary classification task, diversity sampling is looking to sample items that are very different from what has been labeled before, and also different from each other. So here are 5 items that have been sampled to be labeled through diversity sampling. And you can see, at least in this data set, they're the furthest from what's been labeled so far and different from each other. So sticking with our models, one way to look for outliers are things which have low activation in your models, low activation of the logits and the hidden layers. So one of the problems with softmax is that it hides the scale of the inputs. So for example, if you have inputs of 1, 2, 3, and 4, the softmax distribution is going to be exactly the same as if those inputs were 1001, 1002, 1003, 1004. And so you don't know what might be confusing to your model because of conflicted information versus no information at all. And so looking at the average rate of activation across your model is one way of finding something that your model simply hasn't seen before. And then this is evidence that it might be something new or previously unencountered, certainly something that doesn't appear very often in your training data, at least not in a way that it resulted in your model being able to find much information from it. And you can experiment with which kinds of layers you want to look at. Obviously, if it's earlier layers, it's closer to your data. If it's later layers, it's closer to your prediction space. That can be more interesting, but then more likely to be biased towards your current model. Cluster-based sampling is probably the most common method of diversity sampling. And so that is simply clustering your data and selecting from each cluster equally. Representative sampling, you can think of as a variation on clustering. So you can think of it as creating one cluster that contains all your current training data and a second cluster that contains all the data that doesn't currently have a label. And so then you can look at what item looks most like your unlabeled relative to your current training data. So what do you not currently have a label for that looks like other things you don't have a label for? And so especially if you're looking at domain adaptation, this can be a really effective method of quickly identifying the most promising looking items from your unlabeled data in the domain that you're trying to adapt to. Final example is real-world diversity, so increasing fairness with data supporting real-world diversity. This could be demographics relating to people, like gender or ethnicity or languages spoken, or other demographics that you care about in the real world for your data, like maybe time of day, day of week, or other kinds of metadata. And so structured for real-world diversity means looking at, again, distribution relative to your current training data. In this case, knowing that you have other demographic information about your data, looking to see whether your data is representative or not. Something to remember here is that this will depend on your model architecture too. In some models, your data will need to be representative, otherwise biases will be perpetuated. In other cases, you only need a minimum amount of data to avoid biases. So most methods for successful active learning combine the two. Uncertainty sampling alone will tend to pick items that look too much like each other, and diversity sampling alone will pick items too far from the decision boundary. So ideally, you want a combination of diversity sampling and uncertainty sampling that'll sample items like these 5 here. These 5 are all close to the current decision boundary, but they're also far from each other. And I give a dozen or so examples of this in my book. I'll go through just 2 of them here to get an idea of how to combine them. Most of the ways for combining them are fairly simple. You apply one method and then you apply another immediately following. And this is one of those, uncertainty sampling and clustering. So initially, we'll apply uncertainty sampling and sample, in this case, something like just the 50% of unlabeled items which happen to be closest to the decision boundary, discarding the 50% which are further from the decision boundary. Then with those closest to the decision boundary, we'll apply clustering and then sample items equally from within each cluster. So obviously that cluster in the middle would have got way more if we're just randomly sampling, and we want diversity as well as uncertainty. So here we're getting that nice distribution of items near the decision boundary but distant from each other. And this is a really simple but powerful method. Unfortunately, you won't see it much in the literature because most academic papers only look at individual methods in isolation and then compare them for their relative value. And also, it's not probably worthy of an academic paper for the 2 lines of code to pipe your sample out of one method and into another. And that's fair enough for an academic paper, but certainly for practical active learning, it's worth looking at some of these simple combinations. And you'll find that in addition to a number of these being in the book, these are also in the open source code that's released with the book using Python, using PyTorch for the machine learning components. One of the more advanced and interesting recent techniques for combining uncertainty sampling and diversity sampling is active transfer learning for adaptive sampling, or ATLAS for short. So I'm sure you're familiar with transfer learning already. You have a model that is trained on one task, in this case predicting A, B, C, and D. You have some data, maybe only a small amount of data, labeled for W, X, Y, and Z, or Z, depending on where you're joining us from. and then you can train maybe just one new output layer to predict these new labels. And the advantage here is that you essentially get the representations from a potentially bigger data set for A, B, C, and D for your W, X, Y, and Z data set. So what's nice about transfer learning is that it doesn't matter what these other labels are. So these other labels can be something that you derive from the data itself. So let's imagine that you have held out validation data also labeled A, B, C, and D. So we care just about the A, B, C, and D task here. We can put that validation data through our model and then bucket everything into correct and incorrect. So let's say that we got half of our validation data correct, half of it incorrect. We can now create a new output layer to predict correct or incorrect. So it's a binary classification task that's trained on our validation data. And for any new unlabeled items, it is now essentially a classifier telling us with what confidence we can expect all our unlabeled data to be either correct or incorrect. Then we can find whatever is the most highest confidence of being incorrect, and we can know that, well, this is something that we want a human to review. Now, if we think our model is getting it wrong, we want a human to validate that. We want to update our training data accordingly, and then that's one of the most likely items for us to be able to increase the accuracy of our model going forward. What's nice about this kind of process is that because we don't know what the actual label is yet, but we don't care about it, we can make this adaptive before we even get that human feedback. So we know that once our model has seen this item, the incorrect item gets a human label, we know that that item and items which are similar to it are going to be labeled correctly because our model is now trained on that particular item. So we can make this assumption that no matter what the label is, we don't know what it is yet, but we do know that it will be labeled correctly, and were that added to the validation data, it will almost certainly be correct again, correct if predicted again later. We can then switch to the other bucket. We can now give it the correct label and retrain our model with this now in the correct bucket. And this will give us the diversity component. So we'll focus initially on the area that has the most incorrect items, most confidently incorrect items. But once we have maybe just a handful of those, which we know that we will later get correct, and then retrain our model accordingly, then it'll start to sample items from other parts of the uncertainty space. So this is a nice way of combining uncertainty sampling and diversity sampling into a single algorithm. And certainly you can have more complicated transfer learning models with more new layers or using different layers into the output layer. But you probably only have a little bit of validation data, and having just a single binary task for your new output layer means you can probably get away without much hyperparameter tuning. And so again, if you look at the example open source code, there's implementations of active transfer learning for adaptive sampling that retrains a new output binary layer like this on the validation data and adaptively samples. In that particular use case, you'll see that we're looking at disaster response, a related example. And so looking at the text should also give you an intuition for the kind of things that get sampled. So finally, just a quick sneak preview into some content from upcoming chapters related to transfer learning. So again, similar to this method of transfer learning, can we take the outputs from one model and use it in another? In this case, rather than retraining a model for a new task, we're using one model as a representation in newer models. So this is what I'm sure you've done with things like embeddings before. What's interesting here, though, is that you might have some tasks which are much, much faster than others. So let's say you want to label A and B, but it's a very complicated task. You require subject matter experts. It takes them a long time to make a decision about label A versus label B. Maybe some sort of complicated medical diagnosis or financial analysis. However, you have an adjacent task, which you know that you can give to crowdsourced workers, and they can do it really high speed. And so while it's not the task you're looking for, it's closely related to it, and maybe you can do that 100 times faster or cheaper, and then use that as a representation. And so there's a really interesting paper here called intermediate training, and it's called intermediate task training because they actually begin with a pre-trained model. And then they use like the YZ model here as intermediate one, and then AB for the output layer. And this really interesting, currently under review work shows that even when they are looking at tasks outside of English, as their AB task in this case, they can do intermediate training on a multilingual model just in English on a semantically related task, and it actually improves the output from non-English tasks. So it doesn't have to be too adjacent to get some accuracies here. In their particular paper, they're just looking at existing academic data sets. But this has some really interesting implications for active learning and annotation as well. You might change your entire strategy in order to get high volume of adjacent and easier to get labels rather than what your target task is. And then you can apply all of the uncertainty sampling and diversity sampling techniques to this model as well. In fact, to both of the models. You might want to look at some active learning within the YZ model in addition to the AB model. And I think we're really just scratching the surface of the possibilities here for the kinds of use cases that we can use for transfer learning and active learning. So it's an exciting new area. So some general advice. Build a system, then refine it. So chapter 2 of my book is a working human-in-the-loop machine learning system with 500 lines of code. There's some basic uncertainty sampling, some basic diversity sampling, a basic annotation interface, and a model that automatically retrains itself every period of active learning. And so doing this, taking it into the second point here, let you look at your data. So you're annotating your data quickly itself. That'll give you an intuition about what's going through and what the best algorithm might be. And then with your working, very simple system, you should also get an intuition about what is the next best step to improve the accuracy. Is it improving the model? Is it improving the annotation interface? Is it improving the active learning methods to sample the right data? It may be that you're already close enough to optimal in one or more of the components of a working human-in-the-loop system. And so rather than try and build state-of-the-art systems for every component of a complicated human-in-the-loop system from scratch, you can start with something simple and build on it from there. Finally, I'd advise to be realistic about time to reach accuracy. It's really hard in advance to predict what level of accuracy you're going to have from your model downstream. So if you can think of a way to productize your human-in-the-loop system that provides value from the get-go, then you're going to be in a position for success.